Hello, this video is about vectors. First I'm just going to talk about vectors versus scalars, what the difference between the two of those are. We're going to introduce some important notation. We're going to talk about equality of vectors. Some terminology, including standard, position, and component form. Also initial point and terminal point. And then we're also going to come up with a formula for a vector from a point P to a point Q. And we'll talk about specifying length. Or the magnitude of a vector in 2 dimensions for right now. Okay, so what is a vector? Well, vectors are quantities that have both magnitude and direction. While scalars are quantities that are characterized by a single number therefore in physics or chemistry, usually the single number has certain units. Notice this one has magnitude and direction. This is just a number. We can almost think of this number like the magnitude. With scalars, there's no direction involved. So a couple of examples of scalars are area. We know the area of something is just a number. The area might be 0, or it might be some other positive number. Same is true for volume. Time is a scalar. Mass is a scalar. Let's see. Temperature is a scalar. Distance is always positive, except for when it's 0. It's never negative. All of those are scalars. Now, some quantities that have magnitude and direction are displacement. It's like distance, but it could be positive or negative, or it could be a vector. You're just going from one point to another. It's a vector quantity. Velocity, here direction matters. The magnitude of velocity is speed, so that's a scalar. Acceleration is also a vector. If you've had physics 1, force is a vector. Are there any other vectors that you can think of? We got displacement, velocity, acceleration, force. That's good enough for right now. So you've probably been dealing with scalars a long time, and you may have seen vectors back in trig. But most of this chapter in this section is about vectors. It's a building block for the rest of multivariable calculus. If I want to represent a vector geometrically, I represent it with an arrow. So it starts somewhere and it ends up somewhere. And the magnitude is the magnitude of the vector is proportional to the length of the arrow. Sometimes if we are not thinking of some physical application, we'll say that the magnitude and its length are the same thing. This one has a certain magnitude, I could measure it. That one has a smaller magnitude, just because it's smaller. Now in general, again, like I might actually be measuring that distance with a tape measure, or it might be proportional to that, depending on what that vector quantity represents. Now if I'm starting at a point P and ending at a point Q, we have a couple of different notations for this. If I start at P and end at Q, we might call this the vector PQ and put a little arrow over it. Often our textbook author, and a lot of textbook authors, like to use lowercase letters with arrows over them, so this might be the vector V. We also tend to use U and W a lot in our book. I've seen capital letters used as well, although not as often as the lowercase letters. All of those could be vectors. And in typed work, like our textbook or your lecture notes, if you just see a bold letter, and it's usually lowercase, like a bold U, I can't really make it bold when I'm drawing here for you, like that represents a vector. Now we say that two vectors are equal if they have the same magnitude and direction. So let me show you an example. Let's say this is the vector PQ. So let's say I start up here at x equals -1, y equals 3. And that's my point P. Whoops, I don't want that point. And I end up at this location. I end up at the point x equals 2, y equals 0. I'm going to call that point Q. So that's the vector PQ. It's one in our picture. And maybe I've got another vector over here. Maybe it starts at x equals 1, y equals 2. We'll call that the point A. And then it ends up down here at x equals, or x equals 4, y equals -1. Now this graph paper that I've just drawn, my white paper, it's not exactly perfect, so that's okay. Question is, are the vectors A, B, and the vector, or are these two vectors equal? Is the vector A, B equal to the vector PQ? Well, do they have the same magnitude? Well, they appear to. I've got, that seems to be the right length, and that seems to be the right length. They seem to be the same as each other. They have the same direction. Yeah, they have the same slope, and they seem to be sloping down. Now, if my grid was perfect, I could just look at it and see if the slopes were the same and those two distances, those two lengths are the same. And I could say that these are equal. But one way to show that vectors are equal, a better way, a more systematic, easier way, is to look at each vector's component form. Now the component form of a vector, at least in 2D, is going to tell us how many units to go in the x direction to get from P to Q and how many units to go to in the y direction to get from P to Q. We use these little, it looks like a less than sign, and it looks like a less than sign and a greater than sign. It's not what it is. It's also not inner product notation, although that looks the same as well. This is just what's it called? The symbol that our textbook uses for a vector in component form. So the question becomes, how many units do I move in the x direction to get from P to Q? Well, I'm at x equals -1, right? And I end up at x equals 2. So how many units did I go in the x direction? I went 1, 2, 3 units in the x direction. So that's 3 units. And how many units did I go in the y direction to get from P to Q? Well, notice our y values went down. Well, I went from y equals 3 to the x-axis, so that's y equals 0. So that's -3 units in the y direction. So that's the vector PQ. What about the vector AB? Is it the same? I'm going to use a different color. Got a lot of colors on my sheet now. Actually, I'll use purple. I'm starting here at x equals 1, and I'm ending up over here at x equals 4. For the vector AB, how many units did I go in the x direction? If I make a right triangle like this, it makes it a little bit clearer. I went from x equals 1 to x equals 4, so I went 3 units in the x direction. And did I go down 3 units in the y direction? Well, I was at y equals 2, and then I went down to y equals -1. So that's 1, 2, 3. That's -3 units in the y direction. So these two vectors have the same component form. So we can say, we can be certain that AB is equal to PQ. Now this is the definition of two equal vectors. If they have the same magnitude and direction, they're equal to each other. But if I want to check systematically, it's helpful to write this in component form. Now this, remember, tells you how many units to go in the x direction. If it's positive, you go in the positive x direction. If it's negative, you go in the negative x direction. The second component in our component form, this is called the y component. So we've got an x component here and the y component here. This tells you how many units to go in the y direction, and because it's negative, it's telling you to go down. So if it was a +3, I'd go up 3. If it's a -3, I'd go down 3. This says go positive 3 units, or go 3 units in the positive x direction. This says go 3 units in the negative y direction, so go down 3. This is either left or right, and that's up or down. But it says start here and go 3 units in the x direction and -3 units in the y direction, and that's where B should be. So I start here, go 3 units in the x direction, -3 in the y, and I end up over here. Same thing for PQ. 3 units in the x, -3 in the y, I end up here. So that is component form of a vector. And again, this is the x component and the y component. They tell you how many units to go in each direction from your starting point. I forgot to talk about what that starting point is. The starting point here, P, is called the initial point of your vector. And the point where you end up, Q, is called your terminal point. Now I'm going to tend to use capital letters for points, even though some other books use capital letters for vectors. Keep that in mind. You know, if it has a little arrow over it, it's definitely a vector. Okay. So I've got the vector PQ and the vector AB. It might be easier, though, if this was written in a slightly different way. So we've got something called standard position. We say that a vector is sketched in standard position if its initial point is at the origin. let's say, I don't need to write that again, sketch of a vector with the initial point at 0, 0. So that vector PQAB that turned out to be the same thing, this vector. If we start at the origin and we go 3 units in the x direction and negative 3 units in the y direction, we end up right there. That's the same vector. This is called standard position. Let's say in general, say I've got a vector v and it has components v1 and v2. v1 is the x component of v. v2 is the y component of v. Those are scalars. They're just numbers, also known as scalars. We've got v1 units in the x direction, v2 units in the y direction. That's what v looks like. So when I see this v1, v2 with these little arrow looking things on either side, that is component form for a vector. If I draw my vector with its initial point at the origin, its terminal point is always at the point v1, v2. So if somebody later said u is the vector 1, 2, I would know I just plot a point at x equals 1, y equals 2. Oops, let's put that 2 over there. And that's my vector u. Okay, now I've been treating PQ, AB, this vector in standard position. I've been treating all of these as different vectors, but they're equal vectors. It doesn't really matter where we draw them. Rather than thinking of this as a vector and this as a vector and this is a separate vector that all happen to be equal to each other, we're going to say that those are the same vector. So we can take any vector that we want and we can move it. We can move it around the xy plane. Some people say when you are talking about the vector, say 3, negative 3, like this one, you're talking about a family of vectors. In our class and in our book, we're going to treat those all as the same vector, just starting at a different place. So this says wherever you start, it does not matter where you start. Go 3 units in the x direction and negative 3 units in the y direction. Or no matter where you start here, go v1 units in the x direction and v2 units in the y direction. Now let's say you have a point P. It's located at x1, y1. And you have another point Q at x2, y2. Oops, that's what it's supposed to be anyway. That's Q. And you're talking about the vector from P to Q. The question might be, okay, well, if P is the point x1, y1, and Q is the point x2, y2, what's that vector in general? Well, we can make that triangle again, just like we did on our example problem. Make a right triangle with sides parallel to the x-axis and the y-axis. And this tells me how many units to go in the x direction, and this tells me how many units to go in the y direction to get from P to Q. Let's think about it. In general, what's this distance? Well, it was easier on the other page, wasn't it? When I was looking at this distance, there was a 1 here and a 4 here. Well, the distance from here to here had to be 3, right? I just had to take the 4 and subtract the 1. That's the same thing that I'm going to do over here. I've got x2 and an x1. That's 10 and that's 1. This distance must be 9. That's 12 and that's 4. This distance must be 8. In general, if this is x2 and that's x1. I'm going to take this number and I'm going to subtract that number. So there's x2 minus x1 here. Similarly, I've got this y value and this y value. I want to know what that distance is. If that's 5 and that's 2, I just get a distance of 3. I do 5 minus the 2. In general, I'm going to have y2 minus y1. So the vector PQ, where P is this point and Q is this point, is given by x2 minus x1, that's its x component, and y2 minus y1, that's its y component. Now, just as a mnemonic device, a memory device, a lot of students say we're doing terminal minus initial. Basically, you're taking the components, or excuse me, the coordinates of Q, the x2 and the y2, and you're subtracting the coordinates of P, coordinate by coordinate. And then you're making those differences the components of the vector PQ. Okay. Now let's talk about length. If this is the vector V, and V has components V1 and V2, its length, also known as its magnitude, it's just the length of that vector there, the length of that line segment, that directed line segment that we're representing with an arrow. That's easy to find using the Pythagorean theorem. I know that this is V1, and this number here is V2. So we've got a V1 here and a V2 here. And then by the Pythagorean theorem, this squared plus this squared equals this squared. Now, so I got V1 squared plus V2 squared equals the magnitude of this squared. Now there are a couple of different ways to write that. I'm going to write it with just what looks like absolute value bars. And if I want to get the magnitude or the length by itself, I'm going to take the square root of both sides. I'm going to write it in a slightly different order. So that's the magnitude of V. So you write it that way. Our textbook, many textbooks also write it this way. This means exactly the same thing as this. I know that looks like absolute value, and you might think that that's ambiguous, but if you know that that's a vector inside, you know that you're finding the length or the magnitude of that vector. And it should always be clear, either because of the boldface or the arrow or the fact that you actually see the component form of the vector inside. These are both two different ways to represent magnitude. I'm going to tend to do this because it's shorter. You know, there's 2 lines on either side here, and there's only 1 line on either side there. But it's exactly the same thing. So if I want to find the magnitude of a vector, I just do this. Magnitude or length of a vector. So I'm taking the components of V. And this is what I say to myself every time. Square them, and then add them, and take the square root. That's it. Very easy. So if I've got the vector V equals -3, 4, you can see it coming, can't you? Side lengths of a special triangle. The magnitude of that is this. I take -3 and 4, I square them, I add them, and I take the square root. It's 9 plus 16, it's 25, square root of 25 is 5. So the length of this vector is 5. We'll talk about one more thing. It's a very important point. vectors versus points in this class. If you see this notation, V1, V2, with these braces on either side, and you see this notation with the parentheses on either side, this represents a point. This represents a vector. V1 and V2 are called the components of V. This is the x component and the y component. I wrote x1 and y2. I'm sorry, that should be x and y, or just x1, y1. Those should match. Sorry about that. Now, x1 and y1 are called the coordinates of the point P. So make sure you distinguish between those two. We cannot add vectors and points. It doesn't make sense. It doesn't even make sense to add points. Points are just locations. This is a location. This is a vector. It tells me wherever I start, go this many units in the x direction and this many units in the y direction. That's where you're going to end up. You're going to have an arrow that starts at one point and ends up this many units in the x direction and this many units in the y direction away from there. That's where the arrowhead will be. This is actually a location in the xy plane. So keep that in mind. And that's it for this video on the introduction to vectors.